strongly in the value of ecoeconomics, and during the past decade, he has developed an energy management strategy that includes a cogeneration project, which currently provides a portion of their electricity, heat, and air conditioning requirements in conjunction with 2 on-site wind turbines. Without further ado, Mr. Bechtold. Thank you so much.
Thank you.
I appreciate it.
All right, thank you, everybody. And I'm going to take about the next hour or so and share with you, at the request of Jeff, my story. And that's tough to do. When somebody says, just tell your story, it's like, yeah, well, it's 75 years old. Where do you start? What do you include? What do you leave out? So I decided to focus on 2 things. What is a Harbeck, and what do we do about sustainability? Can everybody hear me okay? Great. So let's begin. So basically, we just heard that Harbeck is a precision component manufacturer, primarily polymers and metals, and addressing high-end industry. We're not a commodity molder. We don't do spoons and combs and stuff like that. We do what all those people don't want to do because it's too difficult. These are examples of the types of customers that we have, and you'll notice a concentration of aerospace and medical, because those are the 2 markets that we have evolved to focus on, because it's where cheap isn't the best and final answer. It's where you need more than what you can get from offshore, and so that's where we focus our attentions. And basically, I'm going to be reviewing a 45-year-old story that is how long ago, 46 years actually, in September, we started Harbeck. And it's an interesting thing that in one man's life, one toolmaker's life, got to see all of this change, which is that in the 60s when I started, the most sophisticated tool a toolmaker had to make tools with, molds, precision machine parts, and all of that, was called a Bridgeport, which probably many of you are familiar with that term. And the most sophisticated Bridgeport was one with a power feed. And that power feed would go between, in one direction only, 2 stops. And that was incredible. So because you could make it proceed at its own pace that you could control and then go do something else. So it made you more productive by having this, what now is hard even to find. But then in the 70s, they introduced numerical control. And now they're using 1s and 0s to control machine tools in all directions. But 1s and 0s in those days was primarily accomplished by paper tape, punch cards, eventually magnetic. But so the 70s was the evolution of that. And then in the 80s, late 70s and 80s is when they said, you know, we could just put the computer right on the side of the machine rather than having all of this extra, and they did, and it worked, and that became CNC. And then in the 80s, they said, now that we have this ability to move this thing in any direction very accurately, very repeatably, very reliably, how are we going to make it do even more powerful and all that? And that's when CAD-CAM came out. And CAD-CAM gave us another computer that could initially do line drawings, eventually do surface, and finally do solids. And so in the evolution of CAD and then CAM to support it all the way through, we end up today with an amazing combination, again, in one man's lifetime. But all of that is called subtractive today. The rest of it, and so for us, a very long time we've been involved in this since the late 80s, and that is additive, often referred to as 3D printing, but in our world you have subtractive and you have additive. And the future, we believe, is a combination of both, and that's what we're trying to master right now. So as an example, we have most sophisticated metal growing machines, complex polymer machines, polymer FDM machines that can grow polymers that are difficult to injection mold even, much less 3D print. And then blends of materials. The one on the bottom is a machine that uses carbon, Kevlar, or glass fiber mixed in the filament, if you would, so it can do, in the end, parts that compete with 6061 aluminum. So now, and that's a very big thing in our world for tooling, fixtures, all of those kinds of things. So now we have a thing that you can put in the solid model at night, come back in the morning and take your tool out of it, and perform just as well as a totally machined aluminum part. And interestingly enough, during this 45-year-old saga, in the very beginning of it, it was true that engineers thought tool makers were incapable, and tool makers thought engineers were idiots, because they would come up with the most ridiculous things that anybody would know you can't do that, but not the engineers. And so the point of this slide is to show you it still exists today. Those are available on the internet at Amazon, and the difference and why I'm pointing it out is from a tool maker's perspective, I noticed that. And I thought, rather than join that club of everybody, I actually have some coffee here. Thanks, though. Rather than join in that conventional lack of wisdom, we wanted to be different, and we decided to make heroes out of engineers as tool makers. So whenever an engineer would give us a ridiculous requirement, or that doesn't make any sense, our job, we always worked together to make sure that we encouraged each other and all that. Don't do that. Don't take a cop an attitude about thanks a lot. The engineers being idiots, because okay, thanks. So that was it. We want to make heroes out of engineers, and I can tell you after 45 years, it worked real well, because we have all of our work is about making engineers successful. And so in the early days, there's two types of prototypes in the prototyping world, model world. One is a concept model, and that only needs to be responsible for a photo shoot, a commercial, a display, but never used, or doesn't matter. But the other one is an engineering model, an engineering prototype, and that one, everything is about detail. So the material exactly the same as production intent, the process exactly the same as possible, the tolerances, everything as close to production intent as possible, and then usually multiples of them, because they're going to take the components and put them in the engine or whatever the device is, and then really test how well they'll work. So in the beginning, the only way we had to make those was by carving them with 3D milling machines and lathes. And so you see examples of some of that work there, but like I mentioned, a lot of times they needed more than one. And so then we also got involved in rubber molding in the early days, and these was a process where we would make a master, and then we would encapsulate it in silicone rubber. When it cured, we opened up the rubber and had a cavity and core so that we could actually mold multiples of them. And each of these rubber molds would give you about 25 parts before they gave up the ghost, and so that was a very big step from carving every one to now carving one and getting 25 at a time out of these rubber molds. But there was a huge compromise. There was only like 2 materials that you could cast parts out of, and they were very limited in their real true engineering characteristics, so there was a trade-off. And then came 3D printing. And so by the mid-90s, when it was out of popular science and into actual thing that you could buy, we were one of the first people to start exploring this. And in the early days, we still have this machine, don't use it anymore, but from this period of time, one of the most brilliant solutions of all the 3D printing that exists today is represented there. It was called the ballistic particle manufacturing machine. It was 5-axis. And at that period of time, which was revolutionary, but it died from undercapitalization. And so they had a great potential, but not enough money to get momentum going to survive and get into production. So they didn't survive. There's actually the machine, parts that we've grown on it. It uses monomer, so no polymer yet, but basically waxes to build the parts up. But that's okay because we can encapsulate those parts in the rubber molding, so that was still a good value. But then the next level came out, and that is what's called the Sanders machine. And now you can see that piece of jewelry there, amazing detail, a huge jump up, let's say, from what we had available till then. Very nice finishes and all that. Again, if you're going to rubber mold it, that's a great tool to make a master out of. So this kept us going, and into the early days when everybody else was saying, what am I going to do with a monomer part, a wax part or something? But for us, it had value. And then eventually, the technologies grew to selective laser sintering. And now you're using an engineering polymer, nylon was one of our favorites, and you're creating a melt pool with a laser beam and literally growing the part by similar to when you injection molded it, but a little slower and layer by layer by layer, but you're melting all the stuff and making it stick together into the shape that you want. And the neat thing about this particular technology back then was you could do both polymer and metal in the same machine. Today, I don't think there's any sintering machines that offer that. They're either one or the other. So it gave us great success in polymer, minimal success in metal because it had a trade-off of materials. It wasn't, while it was dimensionally predictable and accuracy, it had a factor called droop and sag. So you never could tell, for example, which way it was going to kind of twist or lay down. So it was less than what we needed from precision mold making. But again, it gave us that hand squeezer exerciser there is still in our company today. It's been squeezed thousands and thousands of times and still performing perfect. A more contemporary example of its potential is those reactor units that go down into microreactors for medical purposes, and each one they'll put a whole rows of those in. So the impeller that you see on the bottom is actually driven by the top shaft you see there, and that's all grown in one piece. So that it spins and operates and doesn't leak and all of that. If you were trying to assemble it and everything, it would be much less reliable than doing it that way. Even some other examples of it, even to show you the Schuyler Tibbetts, that's a award, an innovation award that's given out every year. I forget the designers group that uses him to do their awards, but that is probably 15 inches by 18 inches size. And there's no way you could make that except for growing it to show the extremes. And it's actually the result of a mathematical algorithm. So if you run out the algorithm, you get that part. Then again, metal, we were limited, successful with that, but you can see on the right-hand side, that's a core for a cap of some kind in a mold. And the normal way to cool it would be to drill a hole through that and run the cooling water. So when you inject your mold, you have to have cooling so that the part will solidify and you can get it out of the mold. And so the alternative, when we grew the part, we sliced it in half to show you, was on the far right side there. That's called conformal cooling. So we're able now, when we used to be limited to only be able to drill a hole in a straight line, now we can make a hole go any place. And so greatly improve the performance of molding because we're improving the cooling as a result of the molds. These are our metal machines today. We had the first DMLS machine in the United States. I tried hard for 2 years before they were in the middle of a patent battle with an American company, and I tried for 2 years to buy one from Germany, but they wouldn't sell it because of that issue. And but when they finally were allowed to bring them to the United States, we got the first one that went to a company. And so that's how long we've been in it, and as a result of that today, we are really a leader in that industry, and we do metals and materials that no one else has done before, and we create dimensional results and combinations of features that no one else seems to be able to do. And that's what keeps us in business. That's what our edge is, always trying to think of the newest possibilities to address the needs in the most advantageous way. Other examples of our additive metal, that piece on the left is actually a screen. Okay, if you look closely, you can see below it, so it had tiny, tiny holes in it. And automotive on the lower right is an automotive part. So now we get into polymer additive. So for metal, the polymer is equally to what I mentioned in stressing to find the newest and greatest in metal, we also do in polymer. And so these are all state-of-the-art machines, from sintering in polymers to the one I told you about with fibers to do compound polymer parts, and all stereolithography, all different ones that print. This one on the bottom looks like they're prints in colors, any color you want it to be, any shape, any color, and all these kinds of things. And then we also use it to research stuff. So still pursuing the way to make more model parts accurately and in the material that they're supposed to be. This is an example of some of the different, the part is this little, oops, I knew I'd do that eventually, is this little thing right here. It's actually the hub for Kidwind wind turbines. If you're familiar with Kidwind, we make their parts. And so we use that as a benchmark. And we take all of the technologies that exist in the additive, and what we're doing with all these different colors is not trying to get colors. Each one of them is a different process, a different machine, a different outcome, and all that. But what we do is keep the same goal, and then we can measure A to B to C to E, D to E, and find eventually the best result. We also experiment with, do you need a solid block? So you see over here, that's a mold block also, but we're taking advantage of the ability to do lightening of the materials, and we have other, and there's more examples of other new tooling technologies that are coming out by additive, where they're actually growing the mold details, right, in the machines and to a higher level, or, and the part on the top there, high engineered polymer ceramics. So they'll withstand the pressures and the heat of injection molding. So a lot happening in that world, trying to make the costs, because the tooling is by far the largest portion of the cost in any plastic part. So whatever you can do to reduce the cost here reduces it. This is eventually where it's going, I believe, and what we're striving to be part of when it happens, and that is, so if you're familiar with fused deposition modeling, and you know the monomer filaments, or not the filaments that are used in several different materials and colors and all of that. But we as a company, as an example, the other extreme, have more than 200 different polymer blends in our inventory. So 200 different kinds of combinations of polymers to meet the market need that we address. And so when we try to translate that into 24 filament solutions that might be available at the most, that's not possible, often not possible. So the dream machine would be if we could take a machine that we could go take some of our pellets from injection molding, put them into another machine that would grow the part for us, and then we could test it, and then if it's good, then we know whether to make the tool or not. This is getting there. So this machine is large. It can probably grow a 3 to 4 foot cube part, but so far all of the machines in the world of pellet to part are doing what they call near net shapes. So they are the shape inside of a rough finish, the excess material outside. So they try to sell you that you will be able to get your part, but you've got to grow it rough and then finish machine it. But we know the technology is there to make the smooth parts, and so we're waiting for the day when we can grow the finished part, or very close as possible to it, from any material in our inventory and go from there. Other examples, so this leads us to today's most advanced things, which is topology and generative design. The part on the left, on the top, is one that we would have created 10 or to 50 years ago for the solution to mount 2 cylinders to a machine or something like that. So you see the mounting, 4 mounting holes, the 2 uprights areas with a cross-drilled hole to mount the ends of the cylinders on it. The part below that is the same part, but it is done by what's called topology. In topology, you take the need. So how many pounds of thrust, how much force, how much everything, and then the computer designs the part for you. And it is, as you can see as a result, amazingly less material. The only reason we had all that material there before was why spend more time machining it away? It's not hurting anybody. But now it's why grow it? It's not any good for anybody. And so you see the whole new generation of parts. And I mentioned we're in aerospace and medical, where weight is everything. And really, we're going into a future where weight is everything for everything, because more weight's more energy. No matter what you're doing with it, the more it weighs, the more energy it takes to use it, and we need to pay attention to energy or else. Again, you can see polymer, metal part in the middle, and then an example of another part done through generative design. Generative design is you don't start with any geometry. You just tell the machine what I want it to be this high and this wide, and I want it to, as a simple example, be a stool. And then you say, I want 10 versions of it, and it will generate 10 different, totally different devices. And then you say, I like this of that, and I like this of that, but I would like 10 more. And then it will take those things and mix them together, and on until you get the desired one, and then you grow it. This is an example of the toolmaker of the future. I mentioned briefly at the beginning that we think it's when they come together, additive and subtractive together. Why we have this idea and why we're trying to push this rock uphill, because it isn't a very conventional idea yet, is because we're mold makers. And even in our pattern making and model making, we're mold makers because we made the other tools that I was telling you about. And in that world, you have an ability in your brain to create exactly the opposite of what you want. So if you think of what a mold is, it's the exact opposite of the part. And therefore, when you fill it, you get the part. And so we know that the human being has the ability to think in the opposite and produce in the positive, or negative and produce in positive. So this is a part that's an example of that. The top part you see here is a core, so the inside of the mold part, for this very precise, very high finished optical lens mount. So there are 3 or 4 mount stations in the inside. You can maybe see the circles in there. They are each one deeper and deeper, and so different lenses are stacked up in there, and then it becomes a lens assembly for something. So the requirements of the part are very high accuracy, very high finish, and it's, again, done in an engineering resin that can withstand the heat of a projector or some device like that. And so you can grow the detail, which you see in the top part there, but the accuracy is only a couple of thousandths plus or minus. And the part needs to be maximum of 1,000ths plus or minus. So you need to have, and it needs to have the high degree of finish that's on there. So the mind of the future, the toolmaker of the future, will be able to say, I know what my additive machine will do. I get this, and in this area here, it's kind of a roughish surface. I know I can't hold that 1,000th times that. So I will build this part, and I will take my CAM or CAD system, say, add 2,000ths on everything. Why more? My mind knows what the CNC machine can do. My mind knows what I can do with a tiniest little thin end mill, 1.5 inches long, to get down into those slots and all that stuff. So why put more on there? And I trust my knowledge of what the machines can do, because they do it over and over, so I know I can build that to that tolerance. I know I can then, while it's being built, so it took 8 to 10 hours to grow that part about that high out of metal, the same mind goes to the CNC machine and the CAM system and says, here's the finished geometry, and I want you to do a one-pass finish cut. So I want you to spin that end mill at exactly the right speeds, the right feeds, and it's going to be 30 thousandths or less in diameter and 1.5 inches long, which is just, I mean, you breathe wrong and they break. So, but yet finish that whole thing in one finest pass. That's exactly what happened. The cutter did not break ever. It took 3 hours for it to traverse that very, very slowly with a high-speed spindle, but the tool maker in this mind of the future knows how to use each to the maximum and to blend them into the things that couldn't be done in any other way in the past. So all of this is about constantly striving to do better, learning the new technologies, bringing the equipment in, trying things when everybody else says, well, who are you going to sell it to? Well, we'll figure that out when we get there. And so that unconventional, perhaps, performance is what got us through 45 years and winning new customers and constantly trying to do better to offer them more. But in that process, we realized that we wanted to be responsible about it. And we could see great differences in levels of companies like ours' attitudes about their responsibility to that. So we decided to make up our own plan, and while we truly believed in the validity of people, planet, profit, we didn't know how to exactly enact it. So in the late 90s, we started down that road when it wasn't even the word sustainability, when it was, the closest thing maybe was green. And in the early days, I made a horrible mistake trying to bank the projects that we would come up with by leading with heart and saying I cared about the environment and inadvertently branding myself as a burned-out hippie or a Birkenstocker. And fortunately, I was pulled aside by a banker friend one time and said, you got to stop talking like this because they're never going to help you, and went back for 6 months, redesigned the whole pitch, all about money. And the good news is it's just as dynamic in saving money as it is about making and saving the planet and energy. So you're going to see about that. Sustainable manufacturing. Now everybody talks about it. And every Fortune 500, you will go to any corporate headquarters, you'll see a beautiful, thick magazine called their annual report. And right next to that, equally thick and beautiful and expensive, sustainability report. And so, knowing that and wanting to know how do we become more sustainable as a manufacturer, I started reading these, looking them up, and interestingly enough, found some of the players who were including their same thick, beautiful examples of wordsmanship. And you might recognize some of those customers there and wonder why I chose them, but of course it's very obvious. Anybody can be sustainable, right? As long as you have a good wordsmith on your staff. Well, we didn't want to do that. We wanted to be the different ones. We wanted to prove everything that we said, and so we set up a management strategy. It included, over time, not initially, but over time we developed all this, a combination of combined heat and power. So we have Capstone microturbine generators that run on natural gas to produce all of our thermal requirements, which are very significant in an injection molding company that does all engineering resins. Because engineering resins are very hydroscopic, almost all of them, and so it's a constant nightmare. Once you open that bag to expose that material to the room, you better hope there's not moisture in the room, because you're going to be cooking it out. It just sucks it all up, and then you've got to cook it all out before you can mold the part successfully. So, and then we also, enamored, I had for years at home, done wind turbines and geothermal and renewable solutions. So I had a level of confidence about what that could do and what I could expect at home, and I couldn't see any reason why I couldn't do it in the company. And then whatever I couldn't, we fought, and eventually, over time now, any one of you can do green energy as simple as so accomplishing the things that I'm going to tell you about by picking up the phone when you leave today and calling your utility and saying, I want green power. And you have the right to it. You can, it's the first and only probably time in your whole life you will ever be able to tell the utility what to do. And they have to go get it. And so the more of you that do that, the more it happens, the more they're forced to go buy renewable energy. So, and then the why bother? You can see some of the beginning talk of the costs there. If I'm saving energy, I'm saving money, because I use a lot of electricity. You can imagine to run 40 plus CNC machines and 40 plus molding machines. It's over 3 megawatt a year, so a lot. This is what it looks like, a brief history of our pursuit of this energy alternative that I'm alluding to. A combination of the first, we were able to do our combined heat and power plant, then we added a wind turbine, then the combined heat and power plant paid off. When we say we paid off, we mean we took the energy that we did not give the utility company for a certain number of electrons and gave it to the bank instead to buy the electron maker. So if it's a wind turbine or a micro turbine or whatever it is, and so were the paybacks the normal ROI everybody in business world knows you should have of 3 years or less? Absolutely not. But I keep trying to help people to understand you're going to pay that money anyway. So if you balk at the fact that a solar roof is going to cost you 6 or 8 years to pay it back, it's because you're paying it with your energy dollars. And you have to pay those energy dollars anyway. So unless you don't think you're going to be here in 6 to 8 years, which that's not a very good attitude for a business that's full of people working there to have. So most everybody, I would guess, thinks they're going to be here. So then we added all the other low-hanging fruit like LED lights and installations. You'll see little examples of all of that. And we have many, many, many ideas for the future. We just did a huge geothermal expansion, and it's a never-ending pursuit of doing more with less. And every time we succeed at it, we make ourselves more competitive. How do we measure it? How do we prove it? Because we're reading all these fluffy stories, and we needed a way to be precise about it, and that we found in ISO 50001. It's a DOE-sponsored world. ISO is world. So a standard about basically less energy per widget forever. And when you say that to people, it's not uncommon that they see forever. That's a big word. But after all these years of involvement in it, I'm absolutely convinced it is forever. And you'll see the different ways that it affects the inevitability of less energy per widget forever. 50,001 accomplishments. In 2013, we became one of the first companies to do that. I think we were in the first class that DOE offered. If not, then it was the second. But then we were also one of the smallest companies ever, and still today are, to get platinum rating, which is the highest rating that they have. And also, we are SEP, Sustainable Energy Partner, which means, so you can be ISO 50001 certified by writing the books or the pamphlets. If you want to be SEP, you have to voluntarily do a third-party audit every year. And that's really the rubber meets the road. That's the proof from an independent party that you're really doing what you say you would like to do. And so that was a perfect answer for us when DOE came out with this, and we jumped on as quick as we could. But just on the bottom of that, to mention a small fact, why bother? As an example, I talked about 5% of or 6 to 7% of cost of doing business earlier. A 5% margin so you see on the bottom marker there, energy reduction had saved Harbeck a minimum of $84,000. Bottom line. There's other way to put $84,000 on the bottom line of a small manufacturing company like ours is to go do $1.7 million of work. Because if we have a 5% margin year, that's a primo. That is, everything is working excellent, and we have great profit sharing. So many, many years we didn't even have that. So if you have something that's talking about a margin impact like that, it's incredibly significant. So quickly now to go through them, we have the combined heat and power plant original version. So when we first started out, we had the 25, 30 kilowatt generators, and we learn about thermal. And thermal is the most amazing thing that everybody doesn't know about. And I say that because, as an example, everyone who comes through that combined heat and power plant for all of these years, I make sure I tell every one of them, from grammar school to business people, one thing. And I say, when you go home tonight and you flip on your kitchen light switch, to put it into perspective of why do we have all of this for the thermal. When you go home and flip on the kitchen light switch, I don't know where you live, I don't know what your utility is, but I can tell you, based on the national average, that whatever fuel that utility used to generate the electricity to get to your kitchen switch, 75% of the energy in the fuel went to waste before it got to your switch. And that's the normal world that we live in. And so I ask people, how do you think that's possible? Well, the ones that even believe that it is possible say, line transfer loss. Small amount. It is significant, but very small compared to the majority. The majority of it is thermal. Why are utilities always located on rivers and lakes and ponds, or have the big inverted mushroom chimneys in their backyard? Because they want to get rid of waste heat. And it's not waste. And it doesn't need to be wasted. And the fact is that we have in this company of this size, now over 100,000 square feet and 150 people, no air conditioners. I remember I said we hold our I didn't say the degrees, but we hold our temperature and humidity to plus or minus 2 degrees. We have no air conditioners, no boilers, and no furnaces. How can you do that? Because they are our thermal potential. So we run those, what would you call them? You'd call them electric generators, right? But to us, in the first few months, they were for us also. And then prices started fluctuating, and the gas, and we went from $2 in a couple of years to $12 a decatherm, and all these kinds of things happened that, in spite of ourselves, taught us the real value of combined heat and power is the thermal. So we now call our company, that we say we are thermally enlightened. We use them only to make heat. Of course, well, how does that got to do with air conditioning? Because the heat energy from those drive absorption chillers. So all of our air conditioning, to hold those tight tolerances that I told you, all comes from the heat, the waste heat, I don't think so, of generating the electricity. The electricity then becomes the byproduct. And so we have learned very much, and it's become a very significant thing. And then about 8 years after we were done with this, I sort of had a new grant for, and now everybody's getting the idea about this thermal. They offered a new grant to improve existing combined heat and power plants to get more thermal out of it, to get as much as possible. And so we were able then to change it. We kept part of our old turbines and added in 8 new C65 turbines. They were even more efficient because in the past, how do we get our thermal? We would run the micro turbines and take the exhaust gas to a heat exchanger and then create this constant supply of hot water. In the new versions, they had, and you can see the up on the top there, that's an absorption chiller. And these are the original micro turbines, and that's the heat exchanger. So we used heavily insulated pipes to take all that heat that we could into that box, tortuous path of baffles, hot water running through the baffles, and when it came out, we created a constant supply of 200 to 210 degree hot water to do all the heating. All of our floors have radiant in-floor heating. To the old parts of the building where we couldn't tear up the floor, we go back into hanging heat exchangers and just blow the air across the hot or cold coils as we produce either the warm water in the winter for heating and the cold water in the summer for air conditioning. That's an example of our website. If you're ever interested to learn more about this, it's a real-time reporting. And not only does it tell you, for example, what the wind turbine's doing at any moment or the micro turbines, you can follow all of the related products and check them for their efficiency and operation and get all the historic data and all of that. So it's a real-time reporting system. And then, so the next thing what we got to do was our wind turbines after the first micro turbines. We put up a 250 kilowatt wind turbine. We are not a good wind site for wind farms. We're only a class 3. They want to be 4 or 5. But because we were going to do wind on site, we had the opportunity to displace retail cost of energy. And retail versus wholesale is very significant. And wind farms can only sell wholesale. So we were able to get like 5 times the value from every kilowatt that our wind turbine did on site. And at the time, and again in the late 90s, early 2000s, wind was so much farther ahead of solar as far as dollars per kilowatt. So for the same amount of dollars spent, I could get 6 times more watts out of a wind turbine on our site than I could out of solar panels. So we went with the wind, and today that wind turbine is literally minutes away from repower. So after 20 plus years, we have completely replaced the generator with rebuilt, brand new specs, so it should have another 20 to 30 years engineering life to rebuild. And that worked so well that when that paid for itself in 6 or 8 years, first thing I could think of was to get another one. And so this time we went as big as we could, and this particular one is an 850. The beauty of wind is it's exponential too, so it isn't 3 times 250, it's 6 times 250, because we doubled the rotor diameter and we doubled actually about 1.5 times the height of it. So the end result is this one produces 6 times as much energy. And remember, this is all displacing retail. So, and because it's on a less than wind farm caliber site, it's much less wear and tear on the equipment. So we're not having the huge impacts that a real world-class wind site would have, so we have less maintenance costs and requirements. Also, in keeping with trying to be as sustainable as possible, all of our vehicles are green in whatever way they can be, from a Tesla to the Nissan Leaf, the Hyundai Hybrid, and where we couldn't find any of those options, we got the most energy or fuel efficient for small transit. There's an example of our in-floor heating to wherever we could. I mentioned every new floor we pour now, every building we build, every addition to our building, has the radiant in-floor heating, which you see in the middle there. That's the floor has not been poured yet. Those are all lines of tubing waiting for the concrete to be poured on top of it. We do daylighting. There's nothing, that is the most significantly appreciated thing that we've done in our company for our employees of all things we've done. That always comes up as the number one thing. So we can't imagine a future where we don't have daylighting of some kind or other. And then we build our walls out of structural insulated panels. So those are 3-inch thick, dense foam, continuously wrapped in enamel-baked steel. So little or no maintenance, literally just slide them together and seal the seam in them, and you have no convection pinch points from normal building methods. So about the most efficient siding solution that you can, construction solution can come up with. And that's the number one rule of conservation is everybody knows what the most green energy is, right? Nope, the negawatt. The negawatt is the one you don't use because you insulated, you put good windows in, you did all these things to avoid. the need of the watt. Again, we did all the low-hanging fruit like everybody else. We did one lighting upgrade in 2007. At that time, LEDs were just coming out, and there was nobody that gave any kind of warranty or guarantee, so I couldn't risk it. But at that time, the new fluorescent technologies were coming out, high-energy ballasts and all that kind of stuff, so we changed out our whole lighting system. You can see that when I say low-hanging fruit, a year and a half it paid itself in electric bill savings. And the important thing to remember, if you're watching any of these numbers that I'm not giving to you just in the essence of time, every one of those is still hitting the bottom line. Every one of those is accumulating and accumulating and accumulating to make positive impact on our bottom line. Then there was a second lighting upgrade when the LEDs finally did hit and were reliable, and we changed over again all to that one. We insulate our molding machine barrels. That's kind of a long story, but historically you didn't do that because these heater bands you see on the left side, the wires that you see attached to them, the heat would destroy them, and you were constantly replacing those, which were very expensive. So nobody insulated their barrels. But eventually, and this is what I mean about ISO 50001 drives this less energy per widget forever, somebody figured out if they could come up with a way to make those last, then everybody who cares about sustainability or energy efficiency would go to theirs, and that is exactly what happened. And now we're able to take a barrel like that, use everyday mineral wool, which are available in any size combinations you can think of in the regular building supplies stores, and then wrap it in galvanized steel and a band clamp. Everything we do at our company, thanks to NYSERDA teaching us this for years and years with opportunities called EIP, Energy Efficiency Programs, we learned that along with every one of the standards that we think about, we also got to add in energy. And so we do energy projections on what will this use versus this one that may be cheaper, but in the long run, is it really going to be? And so we've learned to think about that in everything that we do, and also implement things that maybe weren't necessary, like soft starts on bigger motors and inverter drives, things like that that make, not only do they make the machine use less energy, but they also make less impact on the machine. So your maintenance is significantly reduced as a sign of a reward. These are some more of the things. This is a slide that we give to our employees every year because we want to be accountable to them. You can see the plastic waste reduction, how much we recycled, how much we were able to reuse, our wind production. This particular year, the 250 was broken, and so you can see that, and we were waiting to find a replacement for it. And so you can see a very significant amount of money, that $160,000 did not hit the bottom line because we had to buy that power from the grid. And that's a really good example, again, of that impact. And we produce, anything we can't produce ourselves, which ends up being about 20% of our total every year, we buy green power from the grid. We also, after a couple of years of learning about carbon responsibility, decided to do it with water. It doesn't make a lot of sense economically in our area because we live about 2 miles from Lake Ontario, which happens to be the greatest source of fresh water in the world, and so nobody gives a hoot about water. It's ridiculously cheap. Everybody wastes it. But we also have a sister company that's involved in developing world problems with water. So we have a sense of responsibility and respect for water that perhaps many don't. And from that, put ourselves responsible to only use potable water. By that we mean energy water. Took energy to get it, energy to clean it, energy to deliver it. So the stuff that comes out of your faucet isn't like you've just dipped it out of the stream. It took a lot to get it there. And so we have a respect for it. We hold ourselves accountable to only use that water, which normally in industry is so grossly wasted because of one huge waster, which is called evaporative cooling. So normally that water is just sprayed onto plates, the hot water runs through them, evaporation takes the heat out of the hot water, and you deliver cold water back to the company. So we have So we hold ourselves responsible not to do that. Only thing we allow ourselves for potable water or city water is hand washing and drinking. Everything else, whatever you do use it for, and we have to use some of it, we go to the market just like we do for the fuels that we use in our vehicles. We go to the market and buy offsets for the water that we didn't use, it made an exceptional use for. We also are very big in biopolymers, not biodegradable, because that is one of the biggest marketing scams going. It's very, very hard to correctly compost any polymer, and most polymers, not at all. And we live in a world where the beauty of the polymer is its strengths and long-lasting capability. To us, wanting to make a biodegradable polymer is like saying, I want to have a carpenter build me a beautiful china cabinet, and before I pick it up, make sure you insert the termites. So I make sure it only lasts for so long. And so we aren't about that, but we are about, and this is a very exciting thing that's coming a reality in the world, is bio-origin engineering resins. So instead of using fossils to make the plastic, there's a whole world of science now about using organic materials, sugars and fats and oils that come from nature and are replenishable. So we have a great program about offering our capabilities to the people who develop those materials. We also do things like sensitizing stakeholders. I'm going to move quickly now because we're running out. We not only quote time, material, and carbon, which you can see in this, here it is, to our customers, which that takes an explanation because they don't have any idea why we're doing that. But then to take that one step farther, we also send them a quarterly statement congratulating them on how much carbon did not go into the atmosphere because of their choice to pick Harbeck. And this is one of the most recent projects. During COVID, to do this water responsibility I talked about, we have built a reservoir. We do rainwater harvesting to come up with the other water that we want to use instead of the potable water. And in this case, during COVID, we drained our pond to a couple feet deep and hired a geothermal company to build 2 enormous rafts like you see there, and which basically covers the bottom of our pond and then sunk them to the bottom of the pond. And we did that from the experiment we did over the few years. Here's a small unit that's about 10 feet long and 4 to 6 feet high, and it's made up of 5 basically fin-and-tube heat exchangers or radiators. And we experimented in this pursuit of not putting so much water in the evaporative cooling I was telling you about by running it into the pond. And at that time, we were raising fish in the pond. We thought that was going to be a really nice thing for employees to enjoy. No employee ever fished in it. So when we did the new project, the fish took the back seat and whatever. But what we didn't know at the beginning was, would we make the pond too warm and would we hurt the fish's leg? Well, that didn't happen at all. And by putting we only allowed 2 degrees to go into the pond, but those 2 degrees, so we interrupted our process loop, put 2 degrees in the pond, all the rest of the heat went to the cooling towers. Just those 2 degrees saved 700,000 gallons of water. 1 year. That's the amount of water that I'm talking about industry uses. And does it have to be potable? We know now not, because we came up with another solution for it. And then we just built a new 30,000 square foot addition, and you can see I'm still following the same rules. There's all the new in-floor heating. Now I put the daylighting on the top, just beneath the roof. And the reason why is because the roof is a candidate now for 250 to 300 kilowatts of solar. So it's built with everything to enable that when we can afford to do it. So what's next? I probably talked about a few of these things already. Energy storage. We've been fighting now with our utility for more than 5 years to put in a battery. Their argument against it is we could have a negative impact on their grid. Our argument for it is we're going to take everything off the grid. So it's a complete just obstacle to future development and improvement, which my whole life has been the story, and I promised I wouldn't say anything bad about utilities, so I'll keep going. Storage, solar, heat pumps, all of that. And in the end, this is what we are. We are totally convinced that this eco-economic sustainable manufacturing is eco-economic. It is bottom line impact and planetary impact, earth impact. And I will leave you with one slide. And then just as a favor to my wife, who asked me to, because of you, who you are, and the people that you deal with, I was in school at very best, mediocre student, at very worst, problem student. And so the reasons mostly, I think in retrospect, were I couldn't read very well. And I went through always trying to act up or come up with some reason to never let them know that I couldn't read. Went to reading school, never made any progress, all that. So I am one of the students that tendency of human nature would be to say, oh, God. I'm only telling you that because I loved technology. So and I love that there is STEM now and STEAM, and it's about time. And I just would close with one thought. College is not the only way to a rewarding career where you can accomplish a lot. And so think about the other guys and girls too. Thank you all. And now I have a few minutes for questions if anybody has any, or if you
Kudos to you and your company for your innovativeness, your resourcefulness, and your climate change or climate friendliness. I have a question though, and it is, if I were a young worker and I was interested in coming to Harvard, what kind of background would you like me to have when I arrive?
Oh, I would like, it depends, because I have levels of jobs from production workers to engineers and managers and everything in between, and sophisticated mold makers. But as a very basic, I would be happy to hire you if you just would promise to come to work every day on time. And if you could do math, I have this path for you. And if you could do engineering, and if you could do, so we have a lot of possibilities, but that is the biggest thing of all. It's just get people to come to work every day and want to be there and not stay under cell phone. I mean, we don't even allow cell phones on the shop floor anymore. That's how bad it got, with just incredible. And so it's things like that, just a good attitude and a eagerness to do the stuff. We do on-site training. We have tuition benefits. We have everything we can, and you can study anything. There's no requirements related to your field or anything like that. We pay half the tuition of anything that anybody wants to take, and we do a huge amount of on-site. And we're actually inventing a new kind of skill set. If you remember at the beginning, this additive subtractive in one head person, we're calling it the tool maker of the future, but that's huge potential, and there's no texts. So we're not only will we teach it, but if we can't find it, we'll invent it and then teach it. Thanks.
Okay. Well, thank you very much.
Yeah, you're welcome.
And on behalf of the STEM Hub, we'd like to present you with this plaque and thank you for a wonderful presentation and for a wonderful closure.
You're so welcome. It was my pleasure.
Thank you so much, can we? Just take a picture here. Thank you very much.
You're welcome. My pleasure. Get my junk out of here.
That's okay.
Okay.
That's okay. Thank you all for an absolutely wonderful conference. Couple of notes. Remember the evaluations, and I will send that link out if you haven't responded to those. I'd like to thank our AV crew. Joe and Rick are here this afternoon, and Bill was here last night. They did an absolutely tremendous job. Wonderful. if you have dorm keys, if any of you stayed in the townhouses and have your keys still, Tracy is over on the side. If you can wave to her, she'll take your keys back for you so you can return those instead of going back to the townhouse center where we got them initially. So thank you all, safe travels, and look forward to seeing you soon.